Welcome to this engineering overview on selecting the right air filters and dryers for compressed air systems. Compressed air may look clean, but in reality, it often contains moisture, oil aerosols, dust, rust particles, and other contaminants. Without proper air treatment, these contaminants can damage equipment, increase maintenance costs, reduce system efficiency, and even affect product quality. In this presentation, we'll explore how filters and dryers work together to improve reliability, efficiency, and equipment life in compressed air systems. To understand why air treatment is important, we first need to understand what happens during air compression. Atmospheric air naturally contains water vapor, dust, pollutants, microorganisms, and airborne particles. When air is compressed, its temperature rises, moisture condenses, and contaminants become concentrated. As a result, untreated compressed air can cause corrosion, valve damage, pneumatic failure, and contamination inside the system. This is why air treatment is not optional. It is an essential part of maintaining reliable and efficient compressed air operations. Compressed air treatment follows a step-by-step process where each component protects the next stage in the system. 1. Air intake. Atmospheric air enters the compressor. This air naturally contains dust, moisture, oil vapors, and other contaminants that must be removed later. 2. Compressor with aftercooler. The compressor increases the air pressure for industrial use. The aftercooler lowers the air temperature, causing much of the moisture to condense into liquid water. 3. Water separator. The water separator removes the condensed liquid water generated during cooling. This prevents excessive moisture from entering downstream equipment. 4. Compressed air receiver. The receiver tank stores compressed air and acts as a buffer for demand fluctuations. It also allows additional cooling and moisture settling before further treatment. 5. Coalescing pre-filter. This filter removes oil aerosols, fine water droplets, and small particles. It protects the dryer from contamination and improves its efficiency. 6. Refrigeration dryer. The dryer cools the compressed air to remove remaining moisture. This lowers the dew point and prevents corrosion, condensation, and equipment damage. 7. Coalescing final filter. This filter captures any remaining fine oil droplets and particles after drying. It ensures cleaner air before distribution to the application. 8. Activated carbon filter. Optional. Used when very high air purity is required, such as in food, pharmaceutical, or medical applications. It removes oil vapors, odors, and hydrocarbons from the compressed air. 9. Point-of-use applications. The treated, clean, and dry compressed air is delivered to tools, machines, instruments, or production equipment. Additional point-of-use filters may be installed for critical applications. Each stage improves air quality and reduces the risk of contamination reaching downstream equipment. A properly designed treatment chain ensures cleaner air, longer equipment life, and more stable system performance. Different contaminants require different types of filters. No single filter can effectively remove every impurity. Particulate filters are designed to remove dust, dirt, and rust particles. Coalescing filters remove oil aerosols and fine liquid droplets. Moisture separators handle bulk water removal, while activated carbon filters remove oil vapor and odors. Selecting the correct combination of filters is critical for achieving the required air quality. Proper filtration not only protects equipment, but also improves operational reliability and reduces maintenance issues. One of the biggest threats inside compressed air systems is moisture. Excess moisture can lead to corrosion, valve malfunction, pneumatic equipment failure, contamination, and even ice formation in colder environments. Air dryers are specifically designed to remove moisture before compressed air enters the distribution system. By controlling moisture levels, dryers help maintain consistent system performance and extend equipment life. Simply put, dry compressed air means a more reliable and efficient system. There are several dryer technologies available, and each serves a different application. Refrigerated dryers are commonly used in general industrial applications because they are economical and suitable for moderate dew point requirements. Desiccant dryers are used when extremely dry air is needed, such as in pharmaceutical, food processing, or instrumentation applications. Membrane dryers are compact and ideal for smaller point-of-use systems. Choosing the right dryer technology depends on the required air quality, operating conditions, and system demands. After understanding different dryer technologies, the next important concept is dew point, the single most critical parameter in compressed air drying systems. Dew point is the temperature at which water vapor inside compressed air begins to condense into liquid droplets. Simply put, the lower the dew point, the drier and safer the compressed air becomes. Untreated compressed air may have a dew point as high as positive 25 degrees Celsius, while refrigerated dryers typically reduce it to around positive 3 to 10 degrees Celsius. Desiccant dryers can achieve ultra-low dew points as low as negative 70 degrees Celsius for highly critical applications. Different industries require different moisture control levels. General manufacturing may operate with moderate dew points, while pharmaceutical, medical, and instrument air systems require extremely dry air for reliability and contamination prevention. Selecting the correct dew point is essential for protecting equipment, ensuring product quality, and maintaining long-term system performance. Choosing the right filter is not simply about adding a component into the pipeline. It requires careful engineering evaluation based on the application and air quality requirements. The first consideration is the required air purity class, often defined by standards such as ISO 8573. Engineers must also evaluate flow rate, because undersized filters create excessive pressure drop and energy loss during peak demand. Other important factors include system pressure, oil carryover tolerance, particle size limitations, and operating temperature conditions. For example, food, pharmaceutical, and medical applications often require extremely clean air with minimal oil contamination, while industrial applications may tolerate small traces of oil. Proper filter selection improves reliability, protects downstream equipment, and helps maintain energy-efficient operation throughout the compressed air system. Selecting the right dryer involves much more than matching it to the compressor size. A complete evaluation of operating conditions is necessary to achieve reliable and efficient performance. The process begins with identifying the required dew point for the most critical application in the facility. Ambient temperature also plays an important role, since hot environments reduce refrigerated dryer efficiency, while cold climates may require freeze protection. Engineers must also consider compressor size, demand fluctuations, installation location, and maintenance capability. In some systems, varying air demand may favor desiccant technology instead of oversized refrigerated dryers. Energy efficiency is another major factor. Modern cycling and variable speed dryers can significantly reduce electricity consumption while maintaining stable operation. A properly selected dryer improves reliability, minimizes downtime, and reduces long-term operating costs. Many compressed air systems lose performance because of avoidable design and maintenance mistakes. One common issue is undersized filters. During peak airflow demand, these filters create excessive pressure drop, forcing compressors to consume more energy just to maintain pressure. Ignoring pressure drop across dirty filters can silently increase operating costs every single day. Incorrect dryer placement is another major problem. If wet air enters long distribution pipelines before drying, corrosion and contamination spread throughout the system. Poor condensate drainage allows water to accumulate and re-enter the airstream, while skipping pre-filtration can damage expensive dryers and reduce their service life. Even oversizing the dryer can create problems. Oversized refrigerated dryers may short cycle repeatedly, reducing dew point stability and accelerating equipment wear. Avoiding these mistakes is critical for achieving efficient, reliable, and long-lasting compressed air system performance. As we conclude, let's review the key lessons from this presentation. A compressor alone does not produce clean or dry air. Proper filtration and drying are essential for delivering reliable compressed air throughout the system. Filters remove contaminants such as dust, oil, and particles, while dryers remove moisture that can cause corrosion, failures, contamination, and downtime. Selecting the correct equipment is equally important. Both oversized and undersized components can waste energy and reduce performance. Precision matching is the key to efficient system design. Ultimately, clean and dry compressed air protects downstream equipment, improves reliability, extends equipment life, and reduces hidden operating costs. Thank you for watching, and we hope this engineering overview provided valuable insight into compressed air filtration and drying technology.